So today we start Lecture 5, Part 1, which is essentially Chapter 5 of your text. And I'm not going to go through all of the details of Chapter 5 in your text, but I'll show you the more salient points of the chapter. So the first part of the chapter, we talk about polar coordinates. Now, we're accustomed to rectangular coordinates or Cartesian coordinates. So as you know, when we plot points in the XY plane, okay, which are typically offered are the abscissa and the ordinate, okay, of a point in the XY plane. Well, in polar coordinates, we don't have an XY plane. We have a different kind of coordinate plane, and it's called the polar plane. All right, so let me tell you what the structure of a polar plane consists of. Pretty simple. So a polar plane consists of a point in space called the polar vertex, and then a ray that emanates from the point called the polar axis. So the polar axis is a ray that emanates from the polar vertex, right? And so that's all there is to the coordinate system of the polar plane. And so, like with the Cartesian coordinate system, we want to plot polar points in the polar coordinate system, okay? And so let me demonstrate how to do that. So the format for a point in the polar plane will be given as r theta. So these will be the coordinates. So the abscissa is r, the ordinate is theta. And so both of these are numbers. And so for instance, consider this illustration right here. So let's suppose I have a point in space right here. All right, and say we have an r value of 3 and a theta value of pi fourths radians. All right, so here's how to interpret the information given here and in the drawing. R is a radial arm length. So what you do, the way you construct this point in space is, you start at the polar vertex and you go out a distance of 3. Okay, that will be your radial arm length. And then you depart from the polar axis an angular distance, that is, an angular distance of pi fourths radians. Right? So you rotate counterclockwise pi fourths radians in this direction, okay? And the end point is the radial arm length. This distance right here will be 4 units in length. I'm sorry, 3 units in length. 3 units, I have 3. 3 units in length, and an angular distance of an angular distance of pi fourths radians from the polar axis. Right? So that would be the coordinate of point P. So consider this purple annotation right here. Here I have the polar coordinates of a point in space to be a radial arm length of 1 and a rotation of 3 pi over 4 radians from the polar axis. So the way you would plot this point in space or in the polar coordinate system is you go 1 unit from the polar vertex, and then you take this radial arm and you rotate it 3 pi over 4 radians, okay, counterclockwise. And then this terminal point would be your point in the polar plane. So that's how you plot polar points. So there are going to be a couple of web-assigned questions that ask you to plot polar points in the polar plane, needless to say. All right, so now consider this point right here, the green shaded point. So in this case, the radial arm length is 3. Okay, so you're distance 3 from the polar vertex. So this 3 means a distance, okay, 3 units from the polar vertex, and the angle is pi 6 rotated clockwise from the polar axis. So if you go out 3 units from the polar vertex on the polar axis, and then you rotate yourself pi 6 clockwise, you'll end up at this point in space, and the coordinates will be designated as 3, negative pi over 6. Okay. All right, now consider the blue point right here. All right, so the blue point was obtained by starting at the polar vertex, okay, going out 3 units along the polar axis, okay, and then rotating counterclockwise, okay, 3 pi radians. Okay, so you take this radial arm of 3 units, rotate it counterclockwise 3 pi radians, and you'll end up at this place in space, right? And so the coordinates would be 3 pi. All right. Okay. Now the the abscissa of polar coordinates can also be less than 0. Okay? All right, and so it's a little bit tricky on how to plot polar points where their abscissas are less than 0, as shown in this illustration. All right, and so the technique for doing this is you essentially map or plot, take for instance this point, the first technique you'll do, or the first step you'll do, is you'll first find in space the location of this polar point, P at 4 pi over 4. In other words, you basically take the absolute value of the abscissa of this polar point, okay, which is 4. So then you go out for a distance of 4 from the polar vertex along the polar axis, and then you rotate pi fourths radians. Okay, so you'll end up here. You'll end up in space right here, essentially in a quadrant 1 location. Then what you'll do is, since the abscissa is negative, you'll take this point, okay, and you will rotate it an additional pi radians. Okay, so rotate it an additional pi radians. Okay, and so in this case, oops, a little bit off on the scaling. So rotate it pi radians, and then finally you'll end up at the location in space where your abscissa is negative and your theta value is positive. Okay, so this concept a little bit tricky, but it's explained in this illustration as well. So here we have the polar vertex, the polar axis sketched, and then here we have a point plotted, an arbitrary polar point plotted, which coordinates are r theta. Now, if r were less than 0, okay, then PR theta, okay, for r less than theta, so I'm looking at this note right here, would be essentially a rotation of this orange P 180 degrees or pi radians counterclockwise, okay, and then finally you'll end up at the proper place in space for PR theta where r is less than 0, and theta, of course, I should stipulate that theta is greater than 0 in this illustration, okay, because we rotate it counterclockwise. Anytime you do a counterclockwise rotation, theta is greater than 0. Okay, so that's how you plot polar points, and we should do a couple of examples to make sure that we can plot polar points in all 4 quadrants. Okay, basically by 4 quadrants I mean all 4 rectangular quadrants. If you were to overlay the XY plane onto the polar plane, right? So by overlay, okay, you can kind of see that this mimics, in a sense, the XY plane. Okay, you see how you can overlay the two, and the origin of the XY plane aligns with the polar vertex, and the positive x-axis in the XY plane aligns with the polar axis. Okay, so that's one way of visualizing how things work. Okay, so now, so the rubric is, okay, so if you have, again, I'll emphasize, say you have r and theta both greater than 0, and you plot in space, say in this case a quadrant 1 polar point r theta, and supposing that you want to plot, I think this isn't right, so I would ignore this. That isn't totally correct. I'll explain how to do that later, but anyway, suppose that you wanted to plot negative r theta, okay, so you take this blue point in space, and then again you rotate it 180 degrees, and then you'll have this right here, P negative r theta. But it also turns out, if you don't want to have a negative abscissa for the coordinate specification, you can also specify a positive abscissa, but you'll have to adjust your angle accordingly to theta plus pi. So it turns out that, so we have a relationship here. A polar point which coordinates are negative r theta is equivalent to the same polar point which coordinates are r theta plus pi, like so. So these two formats, these 2 points are identical points. Okay, so you can interchange back and forth. All right, excuse me. Okay, so this was part 1, topic 1. So I'll go on to topic 2. So let me pull up the technical notes here for that, for topic 2. I'll pull it. Now these notes should be on the class website, so that's basically what I'm citing from. So topic 2. So let's do some extended examples in topic 2 of plotting polar points. Let me get the note. All right. Okay, so in this note, I'm going to demonstrate how different polar coordinates represent the same point. So let's start off with this blue point right here. In this case, the coordinates, the polar coordinates of this point would be r is equal to 2, a radial arm length of 2, rotated pi-thirds radians from the polar axis. Okay, so here's my polar vertex, and here's my polar axis, okay, which goes in the positive x direction in a sense. Okay, now let's compare and contrast the blue point with the purple point. Okay, now the purple point has polar coordinates of 2, which has the same radial arm length as the blue point, but it's been rotated 7 pi over 3 radians from the polar axis. So if you know from chapter 2 that if you go 7 pi over 3 radians, okay, this would be pi radians, okay? 7 pi over 3 radians is what? What is 7 pi over 3 radians? That would be 2 1/3 pi radians, okay? So that means we go 2 pi radians, which is 1 circle, plus an additional pi-thirds radians. Okay, so we go 2 pi radians, okay, like so, and then we go an additional pi-thirds radians. So the angular rotation of 7 pi over 3 is equivalent to the angular rotation of pi-thirds because these two angles are coterminal. Okay, and so the fact that they're coterminal and they have the same radial arm length means that the rotation starting at 2, going 7 pi over 3 radians, you'll end up in the same point in space as the blue point. So that's why the purple and the blue are the same point in space. Okay, all right. So purple and blue. Now let's talk about the green point. All right. So again, the radial arm length for the green point is 2. So we come out 2 units, radial arm length of 2 units, and then we rotate what? Clockwise 5 pi over 3. Okay, so clockwise, so this is pi, this would be 3 pi over 3, okay, and then 4 pi over 3 would be 1 1/3 pi, so that would be here, somewhere in quadrant 3, and then finally 5 pi over 3 would land us here. Okay, sorry, I'm not drawing the circle concisely enough, but so the angles pi-thirds and negative pi-thirds, of course, as you know from chapter 2 or chapter 3, are coterminal angles. That means the terminal sides of these angles match up, and then the radial arm lengths are 2, so the terminating points would align as well. Yeah, so let's see here. Now, when we talk about coterminality of the coordinates of polar points, we're assuming that you're taking your angle, the initial position of your angle. The initial position of your angle aligns with the polar axis, and the vertex of your angle aligns with the polar vertex. Okay, and the terminating point on the initial side of your angle will be the radial arm length, which is 2. So you take the initial side of your angle, okay, and then you rotate it through the angle, the ordinate of the polar point, okay, and then you'll obtain your terminal point, which is your polar point. Okay, so that's kind of the way of visualizing it. Now, consider the black point, okay. in this case, the radial arm length is 2, -2. Well, the radial arm length is shown as, I'm sorry, the abscissa is shown as -2, and theta is 4 pi over 3. So to plot this particular point in space, we use the technique from topic 1, and that is we identify a radial arm length of 2, okay? Then we take the radial arm length of 2 and we rotate it 4 pi over 3 radians counterclockwise, okay? And so that would put us here in quadrant 3, okay? So this would be, the coordinates of this point would be, I'm sorry, not R, but P. We should use P. So here we have P, coordinates would be 2, 4 pi over 3. Right, and so the rule is, once you have identified this point, and since R in the original equation is negative, we have to take the point and we have to rotate it 180 degrees counterclockwise. And so when we do so, we'll come back, and this terminal side of the angle will be coterminal with the terminal side of this angle formed by the blue ray. Okay. All right. So that's how we deal with -2, 4 pi over 3. All right. So now we have to consider the case, the orange point, where both the abscissa and ordinates of the polar point are negative. Okay. So do the same thing as we've just done. Identify a distance of 2, +2 on the polar axis. Okay. And then rotate clockwise 2 pi over 3 radians. Okay, so 2 pi over 3 radians would put you somewhere in the third quadrant of the rectangular plane. Okay, and then take this and then rotate it 180 degrees counterclockwise, back this way. All right, so you'll go this way, and then finally you'll go back this way. And then you'll find that the terminal side of this ray, okay, specified by these polar coordinates, would be coterminal with again the blue ray. All right, so that's how you plot polar points. So all of these points, the blue, the purple, the green, the black, and the orange, all represent the same point in space. All right, so let's go on to topic 3. So 1 second while I pull up topic 3. Oops, that's not topic 3. All right, so in topic 3, what we're going to do is we're going to express polar coordinates in terms of rectangular coordinates, and rectangular coordinates in terms of polar coordinates. So we're actually going to flip the two coordinate systems back and forth. So while I pull up the note, so let me show you the procedure for converting between polar and rectangular coordinates. Topic 3. So here, if we look at the illustration that I've drawn here. So here I've identified a point and I've given it rectangular coordinates. Now, we can translate from rectangular to polar coordinates for a point in space, okay? So the way it's done is, what you essentially do is you identify the rectangular coordinates, x, y, and then you essentially construct a right triangle in the xy plane based on the rectangular coordinates of the point. So that's formed by, say, dropping a perpendicular from the point to the x-axis, as shown here, and that'll give you your y distance. And then you have your x distances where the perpendicular intersects the x-axis, like so. Okay, and then the radial arm is basically drawn from the origin of the xy plane to the point P. Okay, and so now you see that we have a nice little Pythagorean theorem structure here. You know, you can readily see that x squared plus y squared is equal to r squared. And we also have the this orange hypotenuse has been rotated. As you can see, it's been rotated from the positive x-axis to get to the point pxy. So the hypotenuse of this triangle is essentially the abscissa of the polar point. And then the rotation is essentially the angle or the ordinate of the polar point. All right, so that's conceptually what's going on. And so the translation then would be how you convert. As you can see that the cosine of theta from the illustration and from Chapter 3 lecture notes is essentially adjacent over hypotenuse. And bear in mind that r need not necessarily be 1. So we can solve for x. So r cosine theta is equal to x. Okay, so now you have your translation. So, and then also you can see that the sine of theta is equal to what? Y over r. And so r sine theta is equal to y. Or y is equal to r sine theta, whichever your preference is. So now we have, and then we have, of course, that r squared is equal to x squared plus y squared by the Pythagorean theorem. And we know that the tangent of theta is equal to y over x. So if we have a point xy, okay, and we wanted to express it in polar coordinates, then we would say that the point would be r cosine theta, r sine theta. Okay. You could do this as well. All right. So these 2 points would have the same information. Okay. So let's go on to topic 4, and I'll show you how you can use these techniques. So let me pull up the note. Yeah. So some examples of converting. All right, so examples, let's see here. Okay, so in this note, we'll talk about rectangular coordinates converted to polar coordinates and vice versa. So suppose I give you a polar point in polar coordinates like this, 4, 2 pi over 3, and we wish to convert this to rectangular coordinates. Well, using the formula, we know that x is equal to r cosine theta, which is equal to, so if we plug in r equals 4 and theta equals 2 pi over 3, we know that the cosine of 2 pi over 3 is negative 1/2. Okay, and so negative 1/2 times 4 is negative 2, so this would be the abscissa of the rectangular point. Okay, and then y, of course, is equal to r sine theta, and so that would be 4 times the sine of 2 pi over 3, which is equal to 2 times the square root of 3. So therefore, what you would write then, if this were a web assigned question, you would write in the coordinates of the point in rectangular coordinates would be negative 2 times the square root of 3. Okay, so these 2 points are equivalent. Now we can work on converting a rectangular point to a polar coordinate, to polar coordinates. Okay, so in this case, here we have rectangular coordinates, 2, negative 2. And so we know that r squared is equal to x squared plus y squared based on the topic 3 illustration, the Pythagorean theorem. And so solving for r, we get r a multi-valued 2 outputs for r, right? R could be 2 on the square root of 2, or r could be negative 2 on the square root of 2. All right, so here's how we deal with this. Now, according to the previous note in topic 3, we also know that tangent theta is equal to y over x, which is negative 2 over 2, which is equal to negative 1. Now, tangent, where is tangent theta equal to negative 1? Okay, so if we consider the xy plane, okay, and in this case, x is 2 and y is negative 2. So that would essentially put us here in quadrant 4. So here is 2, negative 2. And we know that the tangent function is negative in quadrant 4. Okay? And so the reference angle formed here would be, in this case, if we were to use the rectangular coordinates, the reference angle would be negative pi fourths. Okay? Or pi fourths. The reference angle is pi fourths. So for this particular point, we could conceivably, one way of representing the polar coordinates of this point in rectangular would be to do this. Let me show you. So here's my polar vertex. Here's my polar axis. Okay, and so let's take this number for instance, 2 on the square root of 2. And so if I were to go out here, okay, a radial distance of 2 on the square root of 2, and then I were to rotate, say, negative pi fourths radians, okay, like here, I would end up at the same point in space. Okay, I would end up in the same point. So you can see that. All right, now another potential value for theta. So if the tangent of theta is negative 1, now we also know that theta can be 3 pi over 4 as well. Because where is 3 pi over 4? 3 pi over 4 is here, right? And we know that the tangent of theta is negative in quadrant 2. Okay, so here, tangent theta is negative 1 here as well. Okay, now, so for theta equals 3 pi over 4, what we'll do then is we'll take, now obviously, if this radial arm length, okay, so if this distance, where 2 on the square root of 2, right, then this point would not be the same as this point. You can see they're in different quadrants. So what we would have to do is we would have to take the negative of the radial arm length. So the way we would analyze it is we would have to say, okay, take this point right here. We would have to negate the abscissa, right? And so you remember when you negate the abscissa of a polar point, you have to take the terminal point right here. Okay, there's your terminal point, and you would have to rotate it pi radians. So if we were to rotate this pi radians, we would come back around here, right? So therefore, this would be your choice for another coordinate, for another polar coordinate, another polar point representation for the rectangular point, right? And so this frequently happens. It frequently happens that when you calculate the polar coordinates of a rectangular point, you're going to get 2 solutions, okay? 2 potential solutions, because you get 2 radial distances coming out of the solution to the Pythagorean theorem, right? When you take the square root of 8, you're going to get 2 answers, right? And then when you take the tangent, when you calculate the tangent theta, you're going to get 2 answers as well. And so you have to associate which radial arm is with which angle, okay? So you can investigate, say, okay, if I associate 2 on the square root of 2 with 3 pi over 4, well then I'll end up in quadrant 2, and that won't be the same point. So therefore, I would have to affiliate 2 on the square root of 2 with pi over 4, and then run the same test with negative 2 on the square root of 2. Affiliate it with each of the angles derived from the tangent of theta being y over x, and you'll discover that you have to associate one angle with one of the radial arm lengths. Okay, so takeaway is with a rectangular point, and you're trying to convert it to polar coordinates, you'll have 2 solutions. Okay, because of the multi-valuedness of the tangent theta. Right, multi-valued functions. All right, so let's go on to topic 5. So let me pull up the note for topic 5. So now that we can convert rectangular points to polar points and polar points to rectangular points, we can do the same things with equations. We can convert a rectangular equation into a polar equation, or a polar equation into a rectangular equation. So let me show you how that's done. Okay, so let me pull up the note. All right. So in this case, I'm given a rectangular equation, x squared is equal to 4y, which is basically a parabola lying on its side, opening up to the right. Okay, and we want to convert this equation into polar coordinates, or a polar form of the equation. So all we have to do is replace x with r cosine theta and y with r sine theta. So in doing so, we'll have r cosine theta quantity squared, right? Okay, by composition is equal to 4, right here, times y, which is r sine theta. And then completing the square, we have r squared cosine squared theta is equal to 4r sine theta. And then if we divide both sides, of course, by r, we'll have r is equal to 4, and then divide both sides by cosine squared theta, so we have r is equal to 4 sine theta over cosine squared theta. And then after simplifying, r is equal to 4 secant theta tan theta. So this would be the polar equation representation of the rectangular equation, right? Okay, so I think that does it for, is that all for part 1? Oh, okay, so now we can work on graphing polar equations. That would be the last topic. Topic 6, graphing polar equations. So let me pull that up. All right, so show you what kind of results we can get when we convert from rectangular to polar and polar to rectangular, and how they affect the shapes of the graphs. Okay, so let's do that. So let me pull up the note. So for topic 6, all right. Okay, so now consider, suppose we want to sketch the graph of y is equal to r is equal to 5 secant theta. All right, so, and we want to graph this function in the xy plane. Okay, so the technique would be to convert this equation into rectangular coordinates. So secant theta, if we multiply both sides of the polar equation by cosine theta, then the cosine theta would annihilate the secant theta on the right-hand side. And so we'll have r cosine theta is equal to 5. But by definition, r cosine theta is just x. So the equation that we would graph for this polar equation in the xy plane would be x equals 5, a vertical line x equals 5. All right? So now let's consider part B, topic 6, part B. Suppose we want to graph in the xy plane this polar equation. R is equal to 2 sine theta. So squaring both sides, not squaring both sides, multiplying both sides by r, okay, and I'll show you why we do that. We'll have r squared is equal to 2r sine theta. And so this will be a technique in converting from polar to rectangular. Whenever you see a lone r in the equation, you can eliminate the r in the process of converting to xy by multiplying r by r, okay, squaring r in essence, so that when you have an r squared term, the r squared maps to x squared plus y squared. So that's how you can eliminate r. but now we multiplied the right-hand side by r, and we were fortunate that in doing so, the r sine theta emerged, okay, and so we know that that is y. Okay, so we have x squared plus y squared is equal to 2y. Now bringing in the 2y to the left-hand side of the equation, we'll have x squared plus y squared minus 2y is equal to 0, and you can recognize that if we complete the square on the y terms, okay, we'll end up with the equation of a circle. Okay, x squared plus y minus 1 squared, and then after completing the square, you'll discover that the circle has radius 1. So this would be a circle of radius 1 centered at the point 0, 1. So there's your center. So here's the xy plot of the polar equation r is equal to 2 sine theta. All right. Now the next one, can't plot it, but we can convert it from polar to rectangular. And it's done by noting that here's the polar equation, and we replace r squared with x squared plus y squared, and then we have 2r plus, okay, and then we see that r cosine theta is x. So now, here's the technique we often employ. Get the xy terms on the left-hand side of the equation, as we've done here. And so x squared plus y squared minus 2x is equal to 2r. So the trick is, again, since we no longer have any parts of the equation that involve theta, so now we would have to essentially square away the r, okay, to get rid of the r term. So by squaring it away, you'll have to square both sides of the equation as we did here, and that allows us to replace r squared with x squared plus y squared. We could have taken let r equals, the problem is, the reason why we don't use the radical is because we won't get an equation. In other words, we can't just simply replace r with the square root of x squared plus y squared. That won't work. Okay, we prefer to replace r with r squared, and however that's achieved either by squaring both sides of the equation, as in this example, or in the previous example, multiplying both sides of the equation by r. That is the technique we have to do. So when converting from polar equations to rectangular equations, you cannot use radicals. Okay, you can only accomplish it by squaring or multiplying, either by squaring r or multiplying both sides of the equation by r or powers of r. Okay, all right, and we'll see more of those. All right, so that's it for section 1, part 1, lecture 5, part 1. Okay, so part 2, what we'll do for part 2, I'll pause the video here, and I'll move on to part 2. So